Okay, attendance sheet is going around. Looking at the pilot page, homework number 3 and MATLAB homework number 3 are now posted. Okay, these are due 5 o'clock p.m. next Friday. Okay, and again, just keeping in line with what we got going here. All right, is if you look under solutions, we have solutions to homework 1 posted, solutions to MATLAB homework 1 posted. I've gotten some questions about, what all do we need to be turning in on MATLAB? So the two things is on the assignment it says what to turn in. Okay, and then separate from that, the TAs can tell you what to turn in, but actually now that we have solutions posted, you can really get a good sense for what we're expecting you to turn in. Okay, so that's up there. You should be squared away for next week. Next week meaning, I guess, the stuff that's due tomorrow, okay, which is homework number 2 and MATLAB homework number 2. Okay. So that's where we are with course material. Okay, and then I guess last time, we had Dr. Rattan came in and finished up 2-link robot, started vectors, right? Got through the basic definition of what a vector is. Okay, and so today, looking on the course schedule, we got to finish up vectors so we can move on next week to complex numbers. Okay, so that's it. The homework that is posted right now then is all homework on vectors. Okay, homework number 3. Any questions before I move forward? I'm telling you, the turbo motor, senior design project, right there. All right, so who wants to tell me what a vector is? Yeah, it's a quantity, typically a physical quantity, that has to be described by 2 different things. Okay, it's got a certain size to it, what we call the magnitude, and it also has a direction. Okay, and in fact, in this class, we are restricting our attention to 2-dimensional vectors. If you've had high school physics, you might have even done some 3-dimensional type vectors then. Okay, and the key objective of this class really is to understand how to do problems with vectors in kind of a mathematically concise fashion. Okay, and in general, my experience in high school physics is you get a mix of the way vectors are covered. Okay, so I think Dr. Rattan last time talked about the rectangular and polar forms of a vector. Yes? So the idea that a vector can be represented in terms of a unit vector I and a unit vector j. In 3D, you have a third one, a unit vector k. Just for my own entertainment, raise your hand if you used unit vectors I, j's, and k's to do vector problems in high school physics. Not many. Right? Now keep your hands up. The rest of you, raise your hands if you took high school physics. See, so this is it, right? So high school physics is great for introducing the physics, which is actually what we want, right? So the idea that I got forces one way, forces another way. But the problem is, doing even 2-dimensional problems where you just look at the problem and go, well, I can do some trig, and I've got to balance the forces in the x, and I've got to balance the forces in the y. That's okay, but as soon as you move to 3 dimensions now, okay, where it becomes very difficult to draw what is the actual direction, right? And then, if you think of equilibrium, I got to balance the forces so they add up to 0. Well, now when you step up the complexity to dynamics, when you add up the forces in a dynamic problem, they don't add up to 0. They add up to something else, mass times acceleration. Acceleration is another vector on the other side of the equation, right? And so you got 3-dimensional vectors all over the place, not so easy to draw it, look at the trigonometry, and then start balancing things right and left and up and down. We need a more rich piece of mathematics so we can handle vector problems of any level of complexity, right? Three-dimensional rigid body dynamics with vectors. If I'm going to do that, I got to have some mathematical structure. Okay, and so it turns out there's a nice structure for that. It's all based on the unit vectors I and j. And so in this class, you'll get a lot of experience doing problems that you could do by kind of the high school method of look at the trigonometry and see what it is. But you'll realize, hey, I can apply this really mathematical method to solving it, and it almost like magic, it just takes care of the trigonometry for you, okay, which is actually kind of nice. And one of the best ways to illustrate that is with a two-link robot problem. And because you guys, even for homework, right, do this week. You're working on two-link robots, you're trying to solve for the angles, you're using laws of sines and cosines and doing all this trig. You can go back and do the same problems with vector addition, okay? And the trig just falls out like magic, okay? It's kind of neat. So let's take a look at that. Vector addition, we'll start with the two-link robot, but where we're really going with this is we want to look at some mechanics problems. We want to look at forces, we want to look at motions and dynamics, relative velocity, all this kind of good engineering stuff. Okay, so let's start vector addition. Okay, and again, we'll just revisit the well-known case here of the two-link robot. Okay, and so let's say I want to find the tip of the two-link robot, okay, in the xy plane. So here's y and here's x. Okay, and instead of drawing the links, I'm going to draw each link as though it is a position vector. All right, so I'll start here with the motor, all right, at the center. And the first link will locate the tip of that link with a vector. And I'm going to say that that one is at a 45-degree angle. Okay, so let's say it looks like this. Okay, and so here's the next joint. Okay, and so I'm going to say that I know the angle here happens to be 45 degrees. Okay, and I know the magnitude of this one. Right, I'll call this P1. I'm going to write the magnitude 1 over root 2 meters. Okay, so I chose that to be 1 over root 2. Again, I know what the angle is, so just trying to simplify some of the math moving forward. Okay, and then relative to this guy, I will have another link. Okay, and so what I'm going to do, because I'm going to use vectors to represent this, is say if the tip of the link is over here, incidentally, how much is this number, 1 over root 2? Ballpark. All right, somebody pull out a calculator and do 1 over root 2 for me. 0.707, right? So that's 0.7. Let's say that the next link is not the same length. Okay, we'll make it shorter, 0.5. So not a bad idea with vector problems to kind of do things semi to scale so it makes physical sense. And I'll say this one's at an angle of 30 degrees relative to the horizontal in this case. I'll go ahead and locate that here. Okay, so that's 30 degrees there. Okay, and so here's the tip right there. Okay, and here's the idea. I would like to represent the final position, okay, of the end of the second link with a single position vector from the origin. Okay, and so I got 2 P1 at an angle 45 degrees. Then I got P2 at an angle 30 degrees. This guy will say it's 0.5 meters. Okay, and what I would like to do is say, what would be the position vector straight up from the origin all the way to the end? Okay, that's the idea. So I want to know this vector P right here. Okay, what I would also like to know is what is the angle here, theta, relative to the x-axis. Okay. Incidentally, when we did the two-link robot before, right, we were looking at, hey, if I'm at a certain endpoint, how do I find the angles theta 1 and theta 2, right? In that context, theta 2 is the relative angle here, okay? But if I knew the p and the theta over here, could I figure the rest of this stuff out? Right, so the point is, if I can use a vector approach to find the p and the theta, that's an alternative method to solve the whole rest of the triangle. Okay? And so let's see if we can think about how that would work with a vector addition problem. Okay, and here's the way I want you to think about it. To get from the original motor all the way to the end, I can do it more than one way. I can do link 1 at a certain angle, link 2 at another angle, and end up at the final spot. Or I could just start at the beginning, and had one big position vector that goes to the final spot. And so when you look at that picture, what you're actually saying is to get from the original motor to the tip. Okay? What I really want to do is take one vector and I want to add to it the other one. Okay, and this is what we mean by vector addition. Okay, so physically, I've got a vector that gets me here, and I take another vector and just add it right to the end. I add its magnitude and its direction, right to the end by placing it on the end. Okay, and the question is, how does that fall out mathematically? Okay, and so what I want to do is look at each one of these vectors separately like its own little triangle. Okay, and so take a look at what I have drawn here. P1 and P2 each forms a right triangle relative to the xy axis. All right, and so I can think about this as P1 being a vector that has two components. Right? It will have Px1, the x component of P1 from here to here. Okay, and then it has the height, which is the y component, and we'll just label it here Py1. Okay. So the x component of P1, the y component of P1. Similarly, P2 has a horizontal leg, and we'll call that Px2. Okay, and it has a vertical leg, and that's this guy here, Py2. So if you just stand back and look at this for a minute, if I were going to write the entire vector P now, just the single vector, in terms of x and y components, would not Px be this entire distance from here to here? All right, and would not the y component, Py, be the entire distance from here to here? And so really, by inspection, how does the total result, the vector P, okay? So really, I can say that by inspection, the vector P, the answer for the position of the tip, is equal to Px, times the unit vector I in the x direction, plus Py times the unit vector j. Can I tell, if I knew each of these vectors separately, and I had the Px1 and the Py1, and I had the Px2 and the Py2, how would I get the Px and the Py of the final position? So let me make this as simple as I can. So I know Px1 and I know Px2. How would I get Px? Add them up. Okay, so again, just looking at the picture, I can say this is true where Px is the sum of the two components, Px1 plus Px2, and I can say that Py is the sum of the two components, Py1 plus Py2. Okay? And so, bottom line is physically adding vectors, which means take one vector and put the next vector at the tip and include its magnitude and its direction and get to an endpoint. Just from looking at the geometry, I can see that adding vectors means adding the x and y components. Is that clear? Okay, so the conclusion is that adding two vectors basically amounts to adding their x and y components. All right, so the question is, can we use this whole ij method, writing these vectors down in terms of i's and j's, can we use this result that we can see from the geometry here, to just do this mathematically, where I'm not sitting around messing with trigonometry on this non-right triangle, but instead I'm going to write each of these vectors, and I want to add them up. So I want to write this expression. P is equal to the sum of P1 plus P2. And just do the algebra and let the algebra take care of all the trigonometry. So, in order to do this, recognizing the final position is the sum of the two positions, I just want to write each one of these vectors in terms of its unit vectors I and j, and then I just want to add them up. Questions on the big plan here before we move forward? All right, so let's see if you're with me. Help me out. Somebody tell me, by looking at the picture with the numbers given, okay, what's the vector p1? All right, go ahead.
px1 and plus py1.
Okay, so is it just px1 plus py1, or do I need something else here? I need the I and j, right? So it's px1i, right? Plus py1 what? J. So just to recap, right? The I and the j are what we call unit vectors, right? So I is in the x direction, j is in the y direction, and the length of these vectors, okay, is 1. Do I and j have any physical units? No, right? So in other words, the units here are in this number. Px, right, is a position. It's got a length of meters, right? The I is just an indicator of direction of magnitude 1. So you can think of these i's and j's, right, as notation. It's notation that allows you to simultaneously bookkeep two numbers. Okay? Much like in MATLAB, you've already talked about vectors. What's a vector in MATLAB? It's a row or a column of numbers, right? But each number is in a different slot. So this is slots right here, right? The I is one slot, the j is another slot. They have physical meaning. The I means it's pointing in the x direction. The j means it's pointing in the y direction. But the physics is the number, the component, px1, py1. That's the physical quantity. That carries the units. Okay. All right, so do I know px1 and py1 for this problem? Well, I've got the magnitude, right, which is 1 over root 2. Yeah. Do I know what angle it acts at? Yeah. It's 45 degrees, right? Okay, so let's do the math here. So let's write down P1, right? P1 is Px1 would be the magnitude times what? Sine or cosine? This is 45 degrees, so it doesn't matter, right? But in general, if I have an angle relative to the x-axis, the x component is the cosine, right? So px1 will be the magnitude, right? P1, which is 1 over root 2, okay, times the cosine, 45 degrees I, plus py1 is what? The opposite leg of this triangle. So to get the opposite leg, you take the hypotenuse and multiply by the sine, right? So it's going to be the hypotenuse, which is 1 over root 2 times the sine of 45 degrees, and that's in the j direction. So what's the cosine of 45 degrees? You can run this on your calculator, right? And get numbers. Cosine of 45 is how much? 1 over root 2, right? Or root 2 over 2. Okay, and so the root 2 cancels and I get a half, right? So this is 0.5i plus 0.5j. Okay, and does this thing have units on it? The vector P1? Sure, it's meters, right? Okay, so in any vector addition problem, task 1 is to write down the vectors in I and j notation. Okay. Any questions on how I arrived at this for P1? This is the position vector of the first link. You guys with me? Right? And again, the goal is I want to write down P1 and P2, and I want to add them up. Right? That'll get me my final P. All right, so we got P1. How about P2? P2, by definition, should be the x component of the second link. Right? So wouldn't that be Px2 I plus the y component, Py2 j? Take a look at the picture. Right? This is what we're talking about. It's this guy up here. Right? It is just the second link as its own vector now. I want the x component, which is the horizontal leg. Right? And I want the y component, which is the vertical leg. Somebody help me out. X component is what? So it's going to be 0.5, that's the hypotenuse, the magnitude of the vector, times the cosine of 30 degrees. Okay, that's in the I direction, plus Py2 times j. What's Py2? So it's the magnitude 0.5 times the sine of 30 degrees, j. All right, so somebody do the math for me there. 0.5 times cosine of 30 degrees is going to give me what for the vector P2? Cosine of 30 is how much? It's one of these special angles, right? We should know this one. 0.866, okay. So then if I do half of that, I get how much? Yeah, so to 3 digits anyways, 0.433. Can somebody give me an extra digit on that? Is it a 0? Okay, 0.4330i. Okay, plus how about the sine of 30? That's a half. A half times a half is how much? 0.25. 0.25j. Okay, and so that's in meters. So what I got so far is I've got 2 intermediate results. Right? And in fact, like on the first exam, when you have a vector addition problem, one of the parts is going to be write down the vectors. You know, here's the vector diagram, write them down in IJ notation. This is what we're talking about, right? Just the ability to write them down in terms of unit vectors I and j. Okay, so we got the 2 of these guys, and what we want to do now is implement the vector addition. Okay, and so how do you do that? Well, P is the sum, right? P1 plus P2. So the beauty of this is once you write down vectors in IJ notation, you turn a problem that used to be trigonometry into just straight algebra. Okay? So I just plug in the numbers and add them up. All right? So that means the vector P now is P1, that's 0.5i, right? Taking it right from here, plus 0.5 j, all right, that's P1. I'm going to add to that the vector P2. 0.433i plus 0.25 j. See any like terms there? The i's and the j's are like terms, right? Note that when you reduce this thing down to algebra, and you just treat I and j like x's or y's, like terms, what you end up doing is adding what? You add the components, right? It's the reason that this algebra works physically is we observed right from the beginning that adding 2 vectors amounts to adding the components. Well, that's exactly what happens if I just bookkeep the components in terms of I and j, and then I just do the algebra. Right? The laws of algebra automatically take care of it. So let me show the intermediate step here. I'm going to group the terms. Right? So it's 0.5 plus 0.433. Those are the x components, right? I'm grouping the i's. And then I'm going to group the j's. 0.5 plus 0.25 j. Okay, so normally I wouldn't need to see that intermediate step. I just want it to be crystal clear what we're doing here. Okay, just grouping like terms. And then so finally, the vector P, okay, is these 2 numbers, which is 0.933i plus 0.75 j. What are the units? Meters. All right, now, so this is an answer for the position of the tip of the second link, right? The final position relative to the origin is that. What I really want here is I want to know p and theta. How do I get p and theta if I have these two guys, which are px and py, right? The x and y components. How do you go from ij notation to this guy, which is magnitude and direction? Yeah, trig, but it's just Pythagorean theorem, right? Or, right, what we can say is p, which is the magnitude of that vector. Okay. Just to be clear, did Dr. Rattan cover this kind of idea of the notation, the magnitude of the vector, sometimes written like this? Yes, have we seen that? Okay, I just want you to be clear of other ways to write it. So you really need to be careful because when you write a vector in this class, we always put an arrow over the top of a quantity that is a vector. So when we say p with an arrow on top equals something, there better be an I and a j on the other side. The letter p with no arrow is what I've labeled in the figure, which is clearly meant to mean the magnitude, okay? The operation of taking the magnitude of a vector is oftentimes denoted with this double absolute value sign, okay? And so you just got to be familiar with these notations you might see in a physics book, in a statics book later. For us, it's the same thing, right? It is p. So it's the hypotenuse, and I get that how? Yeah, I take the square root, x squared plus y squared, I got the numbers right here, 0.933 squared plus 0.75 squared. Somebody run those numbers for me. 1 more time? 1.197. Does that magnitude have any units associated with it? Yeah, that's meters, right? That's how long the position vector is in meters. Great. So I got the magnitude, 1.197. Okay, and then finally, how would I get the theta? So theta would equal what? So I've got p with a x and a y component, right? So in general, the angle is the inverse tangent of the y, the opposite, divided by the x. Now keep in mind, this problem happens to be sitting in which quadrant? First. So will tan minus 1 work on my calculator? I'm good here. But if I were like over here in the third quadrant, calculator might not be what I'm looking for. Okay, so you want to keep in mind that whenever we do an inverse tangent on a vector, we're always thinking this. It's an a tan 2, right, of py divided by px, right? So in this case, this is the same as tan minus 1 because I'm in the first quadrant, right? So it's tan minus 1 of what we have, the y component, 0.75, divided by the x component, 0.933. Somebody run that guy.
38.79.
So theta equals 38, is that right? 0.79 degrees. Okay, and so finally, if I want to write the vector p, p with an arrow on top can be written one of two ways. It could be written like this. This is oftentimes called rectangular form. Sometimes you'll just call that vector form. Okay, but it's the rectangular form. It's got x and y components. Or this way, p is equal to a magnitude 1.197. And then the way we'll write this is at an angle. Okay, at an angle of 38.8 degrees. All right, if I want to use 3 digits, I'll just go ahead and put the 479 degrees. Okay, and then finally, this entire thing still has units, right? So you tack those on the end, okay, like that. Okay, and so that is another way to write the statement. Okay, this is, magnitude and direction. Okay, but oftentimes this is called the polar form. Okay, and in particular, this idea of polar form and rectangular form, okay, we have similar notation in complex numbers. Okay, and so it's the reason we cover these topics in such close succession is pretty much the same math, okay, in a lot of aspects. Questions? Vector addition. So keep in mind, if we didn't use vectors here, and we just drew the two-link robot, and we asked the question, what's p and what's theta? In order to do that, I'd have to find this guy, alpha, right? Because I know that's 45, right? And if I had the alpha, then I could subtract from 90 to get the theta. So this entire business of the laws of sines and cosines and all the stuff we did before, we'd have to do all that if we didn't have this vector tool. All right, now that we've got the vector tool, I can just look at it and go, I'm not using laws of sines and cosines. I'm just going to do some algebra, and bam, the answer just pops out like magic. Okay? So it's pretty powerful for that kind of stuff. Questions? Vector addition. All right, one of the things I love about this topic is that's it for the math learning objective. Okay? It's being able to write a vector down and being able to add them up. You can do other things with vectors. There's things called dot products and cross products, and there's calculus things you can do with vectors, and that's great. But if you think about all the physics and trig kind of problems you can do with just this, with just writing vectors down and using vectors addition, it's pretty powerful. So let's take a look at a bunch of different applications that have physical context. So position vectors, relative velocity, forces in equilibrium, all those kind of things. Okay, and so let's look at a problem in navigation. So let's say that I have a ship, okay, and it travels 200 miles at 45 degrees north of east. Okay, so we'll call this problem ship navigation. And so I'll describe what it's going to do, and then I'll draw a picture for you. Okay, so the ship is going to travel 200 miles at 45 degrees north of east, and then 300 miles due east, and we want to figure out where does it end up. Okay, find the resulting position. Okay, and so here goes the ship. Okay, we'll go ahead and look at it in general in the XY plane, but keep in mind, in navigation, I'm always thinking about my compass rose over here where I've got north and south, and then I got east and west. Okay? And so that's an absolute measure, north, south, east, west. So 200 miles, 45 degrees north of east. What might that look like? Okay, and so 45 degrees north of east, what does that language really mean in terms of the quadrants here? Okay, so 200 miles north of east, I would think about that being east and then go 45 degrees north of that. Okay, and of course that's the same thing as 45 degrees east of north, right? Because 45 is the same angle either way. Okay, and so the way I'll draw this is going to be a 45 degree angle, okay, and the magnitude will be 200. So you think about this, just like the link problem, this is P1 is 200, right, miles that way, okay, and the angle that we have here is 45 degrees right there. Okay, and then it says 200 miles, 45 degrees north of east, then 300 miles due east. So again, thinking about it in the XY system, due east would be which way? Straight to the right. Okay, and it's 300, so really draw it kind of the scale, bigger than the other one, like that. Maybe a little more, 300. Okay, like this. Okay, so this is P2 is equal to 300 miles, like that. Okay, and the question is, where does this thing end up? Okay, it ends up right here, but can I find the position vector of the entire thing? That's the question. Okay, so in the end, I want to know what's the total P and what's the angle right here, theta. See if I can draw a straighter line. Okay, P and theta. So again, this is another straightforward example of add 'em up, P1 plus P2, the idea of vector addition. Okay, so I want the total vector P equal to the sum of P1 plus P2. So the steps are, can I write down P1, right, in terms of unit vectors I and j? Can I write down P2 in terms of unit vectors I and j? Can I add those things up just using the algebra? And then once I do that, I can get the P and the theta, right, as the magnitude and the direction of the result. You guys with me on the plan? All right, so help me out. P1. Let's see if we can just go straight from the numbers here. Who can tell me how to write down P1, okay, in terms of I and j? Somebody raise their hand. We'll do one at a time. Go ahead, in the back.
200 cosine 45.
All right, so 200 cosine 45 degrees I. Okay, great. Continue. So that's the x component, right? Somebody else want to finish it?
What's 200 sine 45 degrees j?
200 sine 45. 45j. Okay, excellent. So at this point, we can put numbers right in here if we want. Okay, let's go ahead and do that. What's 200 cosine 45? You can use a calculator or it's a special angle.
141?
Yeah, it's 141.4. 141.4i. And of course, it's the same number, 141.4j. Why are these the same number? Because this is 45 degrees, right? If this is any other angle besides 45 degrees, okay, in this quadrant, then those numbers are not the same. Great, so I've got that, and of course the units on this guy are miles, right? This is ship navigation here. All right, so that's P1. Similarly, I can write down the vector P2. All right, vector P2 is what?
300 cosine.
All right, so one at a time. Somebody raise their hand. Who wants to do this one? Go ahead.
300 cosine 45.
300 times the cosine of what? 0, right? So this vector, the angle we're talking about in general for any vector, right, is the angle that it makes relative to the x direction, theta. So this guy is horizontal. So right away the angle is 0. So I can use the whole cosine and sine thing if I want. 300 cosine 0 degrees I plus 300 sine 0 degrees j, right? So the formula works either way, but I could also just look at this and say a vector going to the right is just an I, right? Is that clear? So you can just look at this and say P2 is 300i, and that's fine. Okay, the formulas do recover it, right? Because the cosine of 0 is how much? 1, and the sine of 0 is? 0. Okay, so, just like looking at the picture, P2 is just 300i. That's it. Okay, but if you want to be really exact and think of every vector having two components, then go ahead and do plus 0j. That's perfectly acceptable. 300i plus 0j. Okay, and that's also miles. All right, so finally, if I want to know the final position of the ship, what do I do with those two vectors? Add them up. So let's do that. So again, the vector P is going to be the sum P1 plus P2. So you just plug in the numbers and let the algebra take care of itself. All right, so P1, 141.4 plus 141.4j. Okay, that's P1. And then I add to that P2, 300i plus 0j. And so do I have like terms? I always do. All right, I got i's and j's as like terms, so I can add the 141 plus the 300. All right, so it's 141.4 plus 300 times I, right, plus 141.4 plus 0 times j. And so the final answer for P will be 441.4i plus 141.4 J. Miles, yes, do not forget your units. All right, and so this would be the answer for the position, okay, if I were in vector notation or rectangular form. But if the question is, find P and theta, I need to do one more step, right, because P then would be equal to what? P is the hypotenuse of the triangle, right? So it's Pythagorean theorem. I just take the two components, 441.4 squared plus 141.4 squared. Somebody crank that for me. 463 and a half, 463.5 miles. Okay, and how about the angle theta? All right, let's do the math for it. So it's always, I think about it as an A tan 2, right? It's an A tan 2 of the y divided by the x. So I've got the 141.4 divided by 441.4. Will the tan minus 1 button work for that? Should, right? First quadrant, no problem. Okay, incidentally, if it's not first quadrant, okay, then one of these numbers is going to have a negative sign, one or both. So you can deal with the idea of A tan 2 however you're most comfortable. The easiest thing is probably just to forget the signs, SIGN, use tan minus 1 and realize that you are computing what? The reference angle, right? And you know what quadrant you're in, so you can do the adjustment to give the proper angle. Okay, so that's probably the easiest thing. In this case, tan minus 1 works. So give me a number. 17.76 degrees. Okay, so finally, I could write this guy as the vector P is a magnitude 463.5 miles, right, at an angle 17.76 degrees, right, and again, put the miles at the end. Okay, so both of those boxes are correct answers for the vector P. One of them is in the rectangular form, right, or the standard vector notation. The other one is in magnitude and direction, or the polar form. Questions? Position vectors. All right, so the next thing past position is I can look now at, say, a velocity problem. So let's take a look at a relative velocity problem from dynamics. Okay, so this example will be relative velocity. Okay, and again, you'll do problems exactly like this in ME 2210, which is dynamics. Okay, so I'm not going to write all these words on the board. I'll get a diagram up that'll describe this in a minute. But here's the story. We're going to have an airplane that flies at an airspeed of 100 miles an hour at a heading 30 degrees south of east. If the velocity of the wind is 20 miles an hour due west, determine the resultant velocity of the plane relative to the ground. Anybody ever take an airplane to Hawaii? A couple people have done that before. So usually you fly big airplanes out to Hawaii. It's pretty far out in the middle of the ocean. Okay. Does it take you the same amount of time to get from the mainland to Hawaii as it does going back the other way? Which one's faster? Coming back. Why is that? It's a tailwind, right? So I mean, the way the wind moves on the Earth, right? Generally from west to east, right? And it moves fast up at 30,000 feet at that area of the world. The wind speeds can be 100 plus miles an hour, right? And so if you're aiming the plane into that, okay, essentially, right, the air is going through the engines, right? And you think you're providing a certain amount of speed, and you are in the air, but it's relative to the air. So you're losing 100 miles an hour on the way there, and on the way back, you're gaining it, right? And so big difference, right? So relative velocity, let's think about this. If that's front and back, what if the wind is blowing to the side, right? And so this idea of a heading, that I aim the plane a certain way, right? And am I going to end up where I aimed it? Okay, this is a little harder to visualize, I think, when you think of airflow, but it's true in fluid flow in general, right? Like, let's say you had a river moving, and you had a barge that wanted to get you from one side across to the other side. So you aim the barge straight across, and you go. Are you going to end up directly across? You're not, because the whole time you're going this way, the river's floating you that way, right? And it works the same way when you're flying a plane, right? And so you set a heading which aims you where you want to go, but then the air is blowing you another way. So this is part of the problems when you're doing navigation with aircraft, is you got to have this stuff sorted out when you plan out the trip. Okay, and so again, north, south, east, west. Let me draw a vector diagram of what we're going to have here. Okay, and just to be clear, in a class like dynamics, okay, you'll get a generic figure and a word problem, and it'll be your job to put together the vector diagram, right, that then you're going to solve. This class, our focus is very specific. We want you to be able to use the mechanics of vector addition to solve problems. Okay, and so we're not going to give you a word problem and have you cook up the vector diagram. We will always give you the vector diagram, right? Because we're not testing your ability to do dynamics, we're testing your ability to do the math. All right, so just to be clear. So here's the y and x coordinate directions. Okay, and again, the statement says the airplane flies at an airspeed of 100 miles an hour at a heading 30 degrees south of east. So that means what I'm doing is I'm aiming the airplane at an angle 30 degrees. Okay, and so let's say this is it right here. Okay, so this angle is 30 degrees. Okay, and I'm going to call this VPA. That's the velocity of the plane relative to the air. This is 100 miles an hour. Okay, and then the statement is that the velocity of the wind, right, or the air itself, is 20 miles an hour due west. So what that means is, even though I'm aiming the airplane this way, this is the way I'm actually pointing the nose of the plane, okay, I am now trying to fly through wind that's doing this. Okay? So due west, this is the velocity of the air itself, VA, which is equal to 20 miles per hour. So you can see just by looking at the vector diagram that, you know, the net result of my velocity relative to the ground, in other words, getting from point A to point B, is going to be more or less than my airspeed. It's going to be less, right? I'm going to be effectively ending up here. The reason I know it's less is because the length of this vector, just by looking at the diagram, right, is shorter than the 100. Okay? And so what I'm trying to figure out is this guy, velocity of the plane relative to the ground, VPG. Okay? So here's the dynamics principle, and again, reiterating, you will not be tested on your knowledge of the dynamics principle, okay, in here. You'll be given the principle. Here's the picture, here's the principle. Can you now add up the vectors is the question. Okay, but for your entertainment, let's think about the physics here. So VPG, velocity of the plane relative to the ground, by looking at the picture, I can tell what I'm doing is actually adding these two vectors. So that is VPA plus VA. Okay, so to be clear, let me define these guys. VPG is the velocity, okay, of the plane relative to the ground, okay, which is the one that matters, right? How far on the earth am I moving? Okay, and then VPA is the velocity of the plane. Okay, but it is now relative to the air. Okay, and so this guy is what we call the airspeed of the plane. Okay, so that's my airspeed, how fast I feel like I'm going. Okay, and in fact, we do this in mechanical engineering all the time, right? We test an engine. You can have a certain airspeed and be going nowhere. It's called a wind tunnel, right? I can put an airfoil in a wind tunnel and I can blow the wind over the wing, right? And that's relative to the wing, the same thing as flying through the air. Okay, and so that's the idea. So I can have this air speed, but that's not necessarily the ground speed. Okay, and then finally the VA there, that's the velocity of the air itself, which is really the wind speed. Okay, so velocity of the air itself, which again, the wind. Okay, that's what we're taking into account. So that's the principle. So if I want to find the VPG, again, it's the same skill set. I want to write down each of these things in vector notation, and then I want to add them up. Questions on the context here or the plan before we move forward? Question?
Yeah.
Problem reading my writing?
The word vector was.
Right here?
Yeah.
Relative. Here, I'll write the word out. That's relative. I just did an abbreviation. Relative. Okay? Velocity of the plane relative to the ground.
Question.
Yes?
We concerned with the negative angle and the negative vector?
Well, that's a good question, right? Because ultimately, you know, I want to find the VPG. When I do this, what I'm going to get is an answer with I's and J's, right? But in the end, what you're pointing out is the theta is going to be this guy, right? The total angle from the x down to here will be the theta I'm trying to find. Okay, and that angle will be a negative angle in the context of this picture. Okay, so let's see how the numbers work out and see if it takes care of that. Good? You guys with me? All right, so let's write them down. First step, we want to write each one of these down so then we can add them up. So how about VPA? VPA as a vector, just by looking at the picture. Somebody help me out. This is it right here, right? It's 100 miles an hour, 30 degrees south of east. So 100 cos 30 in the I direction, okay? What about the J? 100 sine 30. Incidentally, the 30 that I labeled here, is that an absolute angle or is that a reference angle? The absolute angle is what? It's a negative number, right? As he pointed out. So I got two choices. I can always think about the sines and cosines of the angle theta. And if I think of theta, it's the absolute angle. If it's a negative, I need to put a negative. If it's over here in this quadrant, I need to put the whole angle. And if I use a calculator, take care of that. When I work a problem like this, you know, can I not just look at the reference angle and make my own decision about what the sine is, S-I-G-N? So I'm looking at the picture, right? So this vector, right, the two components are an x component and a y component. The x component is clearly going in which way, right or left? Right. It's a positive number. How about the y component? That's going down, negative number. So I got two choices, and maybe this was more your question before. All right, I've got two choices. I can think about this as negative 30 degrees and say the y component is the sine of negative 30 degrees. Or I can just think about the 30 as a reference angle and look at the picture and say, to get this vector, I'm going to the right and I'm going down. Therefore, the right is the positive and the down is the negative. Okay, for me, I would do it the second way. Okay, if I were writing a code to do this automatically, I'd have to use the whole angle, right, and know what it is, right? Because it's me looking at the picture that allows me to determine the sine. Okay, so what I would do here is put it as a negative. So it's minus, the number will be what? 100 sine 30 degrees J. Okay, so I have that as plus negative. Okay, you can do this just like normal algebra, right? A plus negative is the same as just doing that, minus. Okay, so either way you want to think about it, you know, honestly, plus negative for me is a little cleaner because then when I group I and j, it's always an x component I plus a y component j. All right, here's the plus. It's the y component that has the negative attached to it. All right, so I prefer actually to write it like that. All right, so let's put numbers on here. So VPA, give me a decimal. 100 cosine 30 is what? 86.6. You want to use one more digit? Is it 60? Yeah, 86.60 I. Sine 30 degrees is how much? All right, so it's a half, so it's minus, so it's negative 50 J. Okay, so 86.60 I, negative 50 J. This is miles per hour. Okay, great. So I got VPA. Halfway there. What's VA? Negative 20 I. Okay, so again, I'm looking at the picture. It's a vector that goes straight left. I can use sines and cosines of angles. If I wanted to say sine or cosine of theta, what is the theta of this vector? Is it 0? Right? The theta is relative to the x-axis. It's 180. So if I think of the x as cosine theta, the sine takes care of itself. Cosine of 180 is how much? Right, so let me write this out to be clear. All right, so we could take the magnitude 20 times the cosine of 180 degrees, I, because that's the direction. Right, but the point is, this guy is negative 1. Okay, and then of course, over here, it'd be 20 times the sine, right, of 180 degrees. J, the sine of 180 is what? 0. So, using the cosine theta for x and the sine theta for y will always work if you use theta defined the way theta is defined relative to the x-axis. Okay, at the same time, this is more complicated than you need to do here, right? Look at the picture and just say, hey, VA, just like she said, it's just minus 20I. That's it. Okay, you can see the picture. All right, so minus 20I. If you want to write plus 0J for completeness, that is okay. Okay, and that is miles per hour. You guys with me? So then to get the total, I wrote down the two vectors. Okay, and I want the total answer, right, which is VPG is the sum of VPA plus VA. I just plug in the numbers. VPG is VPA. I got 86.6I minus 50J, so plus negative 50J. And then I got VA, which is minus 20I plus 0J. And so I add up those numbers. Can I do this without the extra step? Grouping the i's, I'll get 86.6 plus 20, which will give me what? Minus 20, thanks. 86.6 minus 20. 66.6i, sorry, plus 66.6i. And then I got what? Minus 50j plus 0, minus 50j. Incidentally, does that pass a sanity check on what the vector looks like in the picture? All right, the sanity check, the numbers maybe a little bit, 66 and 50, okay, but right, clearly it goes to the right and it goes down. This is the VPG. Now, if I wanted to figure out, right, how long is it going to take me to get from point A to point B? Do I want this, the x and y components here? What do I want? I want the magnitude, right? The VPG. Okay, and I probably want to know where I'm going to end up, which is the angle. Right? So finally, VPG, again, same thing. Pythagorean theorem, I got two components on here. So it's going to be 66.6 squared plus negative 50 squared. Somebody run those for me. 83.3 miles per hour. Okay, that's how fast I'm really going relative to the ground. Okay, and then finally the theta in general, a tan 2, y over x, right? So a tan 2, the y value is minus 50. The x value, 66.6. If I ran that on my calculator as a tan minus 1, would it give me the right answer? It would, right? Because I'm in which quadrant here? Fourth. So let's run it on the calculator. One more time, 36? 36.9? Negative degrees. Okay, so finally, VPG as a vector with the arrow, right, is a magnitude 83.3 at an angle, right, negative 36.9 degrees is the way you would write that, and that's miles per hour. Okay, so again, the basic physics here is I think the plane's going 100 miles an hour because I aim it a certain way and I have an airspeed, right? I think I'm going 30 degrees south of east, but in reality, I'm going 36.9 degrees south of east, and I'm getting there slower than I thought. Okay, and that's, that's the bottom line. Questions? Relative velocity. You can do a lot of cool stuff with vector addition. Incidentally, you could do this entire problem with laws of sines and cosines. Okay, I have at least one homework problem that has you go through a little of that pain. Yes?
If the plane goes slower in the air, how do the pilots figure that out without doing all this complex?
Well, so nowadays, the instrumentation is so advanced enough, right? So it's just like if you drive in your car. All right, whether it's built in or you got a Garmin or whatever. I mean, you can literally know where you are absolutely on the Earth with navigation and GPS and all those things. Okay, so based on that, you could calculate your arrival time in real time based on instrumentation. But it is absolutely true that if you want to do navigation and the way it used to be before we had things like GPS and radar and everything else, you want to take a balloon trip somewhere, you got to sit down and calculate this stuff and figure out which way to aim to end up at what spot and how long it's going to take.
That'd probably take hours.
Well, it's why they used to have people that were navigators. I mean, as the navigators on the ships, they were like the mathematicians of the day, right? Engineers, really. Engineers of the day. Does this make sense, guys? Yes? Yeah. Okay, so the question is, a tan 2 notation, how do we enter that on the calculator? So let me reiterate. There is no a tan 2 button on your calculator. Some calculators, there's at least one person in here with a symbolic calculator that allows them to keep track of the separate signs of the numerator and denominator and will give them the answer. That function is the a tan 2. My calculator doesn't have it. Okay? MATLAB has a tan 2 as a built-in function where I enter two numbers. When I use it on the board in writing, all I'm doing is emphasizing the fact that when I report the angle, I need to report an angle that is in one of the four quadrants, right? And so it happens, the couple we've worked so far, we had a first quadrant and a fourth quadrant. If this guy was over here, then the answer for the theta would be an answer, right, if it were here, between 0 and negative 180 degrees. So 150 something degrees negative is the way I would write it down. Okay, so the idea is, it's that, but honestly, in engineering, as long as we know that you know what the actual answer is. So, for example, could you draw this thing like this? Like that? And do that? That's clear to me that you know which way this goes. Okay? I wouldn't mark that wrong. Okay? So you want to represent the result in a way where it's crystal clear you know what the direction is. If it was in another quadrant, you could write it like this if you wanted to, right? And say it's over here at a certain angle and show the reference angle. Okay? So from an engineering perspective, we're okay with it, but we want you to think, the standard way to write it is always think about an angle theta like this, and then just report the actual theta. If you do that, the engineers are happy, the mathematicians are happy, the computer code is happy, everybody's happy. Okay, in an engineering class, we really care that you just understand what the answer is, and if you make it clear, you'll be okay. You guys with me? It's a good question. All right, so a tan 2 is just my way of reminding you that I'm doing a 4-quadrant problem all the time. Yes?
Now, when it comes to the units of the equations, do you have to, on like an exam, do we have to
Yeah, so here's the rule of thumb on units. Anything that is a requested part of a final answer, okay? Final answer, put it in a box, just like I do in class, we do in the notes. Include the units in the box. The other one you get caught on is if the answer says, plot this on a graph, then the axis labels and the things you indicate on the graph need to have units if they have units. Okay, so anything that is requested as a final answer, in this class we do not necessarily, you know, like right here, I don't have units on this intermediate step. We're okay with that. Okay, it is important that anytime you have a prof, you make sure you lay out what the expectations are. You know, for us, as long as the final answer has the units, we know that you know that it's a physical problem with units. Okay, we don't need to see the units carried through all the intermediate math. Okay, it's a good question. Other questions? All right, great. Let's do another example. Here's the mother lode of statics problems. Static equilibrium, okay? Adding up forces and getting 0. And we got a couple examples like this, and you have actually several for the homework that I posted. I want to say there's 3 or 4 static equilibrium type problems. Okay, and so let's look at this one, static equilibrium. Okay, and you know, this is definitely ME 2120 statics. If you're a biomedical, there's a bio version of statics, but then also physics, physics 2400 as well, general physics 1. Okay, and so here's one. You know, this is a great problem here because the one I've got in the notes, the problem is so simple that if you really understood your high school physics, if you had it, you could actually stare at the picture for a minute, okay? Pull out your calculator and in a single line of calculator punch, tell me what the answer is. Okay, not everybody can do that, but there's a couple people in here that I bet could do that. Okay, and so what we're doing is taking a problem where the physics is so apparent that you could basically deduce the answer, but we're gonna do that problem in a methodical way with I's and J's, right? And the reason for that is, what happens now if it becomes 3-dimensional and all of a sudden I can't look at the picture and punch my calculator? Okay, if I don't have the I's and J's, or in 3D, when we add the K to third direction, then my hands are completely tied. I can't draw the picture, I can't do the problem. Okay, and so this is the reason. We're preparing you for more complicated stuff. All right, so let's see here. This will be a 1,000-kilogram object, okay, suspended from 2 cables. All right, so here it is. Got a cable up top, okay, and the lengths of the cables are such that they will make angles of 45 degrees. Okay, which is what makes this particular problem relatively straightforward to do by, say, a high school physics method. Okay, and so both sides, 45 degrees like that. Okay, and then what we've got here is 1,000 kilograms. Okay, and incidentally, I did this one in the SI system of units on purpose, right? In the SI system of units, whenever they talk about things like weights, they label them in terms of grams and kilograms. Is kilogram a unit of weight? No, it's not, right? It is a unit of what? Mass. Okay, and so now, if I were doing this in the English system, and I said this was 1,000, it would probably be 1,000 what? Does anybody here go to the gym and lift weights?
I don't have time.
Don't have time. They're at pounds, right? Is pounds, right, on a weight at the gym, is that a unit of weight or a unit of mass? Weight. That one's weight. Okay, so you got to keep your wits about you, like what's the language we're using here? If we say 1,000 pounds and we're doing a statics problem, we're talking about pounds of force. That's weight. Okay, I'd have to back out the mass. When we're in English, the tradition is to talk directly in terms of weights as forces. When you're in SI, weight isn't a base unit of anything. You know, the base unit is mass, period. You report something, you know, that has weight, you report that by indicating the mass, and that means you always have to multiply by G. Anybody know what G is? 9.81, right? This is 9.81 meters per second squared, right? So if I take a kilogram and I multiply it by a meter per second squared, then I get mass times acceleration. That's a unit of force. which is a unit of weight. What is that? What's a kilogram meter per second squared? It's a Newton. Isaac Newton himself, right? Named after him. All right, great. So as long as you're aware, just look at these statics problems, and when there are problems that have weights and stuff, if it's SI, you probably got to multiply by G. Okay? If it's English, you know, typically it'll be labeled in pounds, and you already got a weight. Okay? So make sure you're operating accordingly. All right, so here's what I'm going to draw. This is an FBD. Anybody ever heard that saying before? What's an FBD? Free body diagram. Okay, so again, if you haven't had physics, then this is new language to you, and that's okay. Okay, and so free body diagram, somebody that knows what that is, tell me what it is. I had like 20 people yell out, free body diagram. Go ahead.
It's a diagram that just shows all the forces and nothing else.
All the forces. Can you be more specific? Forces acting on it. Got
Force vectors.
Force vectors. All the force vectors.
That are acting on the system that you're studying.
All the vectors that are acting on the system. Close. What do the forces have to be? So let's say I want this to be my free body diagram. Okay, it's going to be the block right here and also this little joint right there. So free body diagram, you can isolate any piece of any physical object, and if that object's in equilibrium, then the forces acting on that piece have to add up to be 0. Okay, but the thing is this rope connected right here to the block? So do I got to put a force here where the connection is? Because isn't there a force there? By the way, this is way beyond the scope of engineering math. Okay, this is mechanics we're talking about, but this is just part of the fun of this class. So the point is, I'm not happy with your definition, right? It's not just all the forces, because I got a force right here too, right? The block is pulling down on the cable, and the cable's pulling up on the block, and if I put both of those forces, they cancel each other out. All right, so the point is, in a free body diagram, you put external forces. Identify the piece and external forces. Any connective forces in between the pieces that make up the body are inside the body. Those are called internal forces, and that's not part of this picture. Okay, so external forces acting on this entire system here is, the question is what's acting? I got the weight of the block, right? So that's mass times gravity is the way I get that. I'm going to call that weight is mg. M is the 1,000. G is 9.81. So this is 9810. The units on that is what? That's newtons. Okay, so I've multiplied the mass, right? The m is equal to 1,000 kilograms, and the g is the 9.81 meters per second squared. So I multiply m times g, I get 9810. So clearly the weight is an external force acting on this thing. And then this thing's attached by cables, right? And so the cables then are pulling this thing and they're holding it up. Okay, and the thing about cables is when I have a problem with cables, I know what the direction is, right? Because that's the beauty of a cable. It can only support force along its length, right? If I try and go transverse to the length of a cable, what does it do? It can't support, right? It's flimsy the other way, right? I can pull on a cable. I can't push on it. I can pull on it, so it's always an axial load and tension. Okay, it's the way cables work, right? And so if the cables were different lengths or whatever, it would change the angle, which would then change the force. Okay, but if they're the same lengths and I lay them out like that, then I'll have two tensions here. I'm going to call them T1 and I'm going to call them T2. Okay, and so what I want to do for this problem is I want to find the tensions in the cables. Okay, so this is a pretty important problem. If I'm trying to hold up something heavy with cables, I got to make sure the tensions are not so big that I will break the cable. Okay. All right, questions about what we're trying to do here before we move forward? All right, so just to be clear, the angle on these guys is 45 degrees, right? Both of these. It's along the cable length. Okay. Question? Yes. Which one? The weight? Yeah, so again, try not to get too tied up in an individual picture. Do I need a plus or minus or whatever? Here's a general rule of thumb. If you draw a diagram that has forces indicated on it with arrows, okay, the sign, S-I-G-N, is built into which way you drew the arrow. Okay, so if I want to represent this mathematically as a vector, and I want to use a standard XY system, then when I write this vector down, I will write it as a negative vector. But in this diagram, it's clear to me that this is down because I drew the arrow that way. Okay? So don't get too tight. If I draw the arrow down and then I also label it negative, some people would interpret that as a negative force this way is actually a positive force that way. Okay? And you start to get confused with double negatives and such. So general rule of thumb, on a free body diagram, if you know the direction of a force, draw it that way and don't add an additional sign on it. Okay? That way you don't get confused. Is that clear? All right, very good. So what we want to do is we want to write this down. Equilibrium. Okay, and it looks like we won't get this problem done, but we'll get it started for you guys and you can look at it. This says that when I add up the forces, the sum, right, this means summation sign, of all the forces is equal to 0. 0 as a vector, 0i plus 0j. So the plan here is I need to add these up. T1 plus T2 plus W, and I need to get 0. Okay? That's the plan. So help me out. We got, what? 2 minutes. Can I write these vectors down? There's the vector T1. How do I write that down in vector notation? All right, this is an important point here because I always get some static, excuse the pun, okay, right at this point. Would it help you any if I just relabeled it like this? In other words, T1, the variable T1 here is the force in the cable, right? It's the tension. What is that on the vector here? Is it the x component? Is it the y component? It's the hypotenuse, right? So keep in mind the way we even label this stuff could throw you for a loop. I would always label it like that. T1 is the magnitude of this vector. It's the hypotenuse. Do I know what it is? I could deduce it, right? The calculator punch I was talking about. Are you ready? Here it goes. Y component of this and this has to add up to that, right? And there's 2 of these, so it's 2T1 times the sine of 45 equals 9810. Solve for it, you're done. Okay? That's it. But this way, I want to write these down. T1 is unknown. So when I write the vector down, I can have unknowns right in the equation, right? So if T1's the hypotenuse, then the x component is T1 cosine 45 degrees I. Is this a positive number here? No, this guy's going left and up, right? So this is a negative plus T1 sine 45 degrees J. So that's T1. Let's write down T2. I'll let you guys do the algebra on your own time. T2 is what? T2 cosine 45I, that is positive. T2 sine 45J, that's positive. And then finally W. Question before, does W have to have a negative? At this point, it better, right? Because the answer for W is what? How much I? 0I plus negative 9810J. I can use sines or cosines, but when I see that it's straight up and down, that's what J is, right? If I wanted to use sines and cosines, this angle would be negative 90 degrees, right? So sine of negative 90 would take care of this right here. So here's the thing. When I take these three vectors, which is half the problem, write these down, and I substitute them in, I'll have two unknowns, T1 and T2. And I will have to add them up to get 0i plus 0j. So when I set the i's equal to 0, that'll give me one equation. And when I set the j's equal to 0, that'll give me the other equation. And I can solve for my two unknowns. Okay? The details are in the notes, but if I were you, I'd go back and finish this because it's insightful. Question before we go. Hang on, guys. Let him ask a question. Yes?
Are the T also in Newtons?
Yes, absolutely. Everything that's a force is going to be in newtons when you're done. Okay? All right, guys. Have a good night.